Hello everyone, my name is Kenlin Liang and I am a PhD student at the University of Massachusetts Amherst. In this video, we are going to present our research work, AI on the Edge, characterizing AI-based IoT applications using specialized edge architectures. This work has been done in collaboration with Professor Prashant Shinai and David Irwin. We first clarify the definition of edge. As we see in the figures, the cloud is large and resourceful data centers. IoT devices could be any end devices connected to the internet, such as mobile phone, smart camera, and smart cars. Edge is physical computing infrastructure that is positioned between endpoint device and cloud. For example, a server attached to an access point, Wi-Fi router, and base station. Compared to cloud, edge is closer to end devices but less resourceful. Edge-based AI workloads is an emerging class of edge workloads, which involves running machine learning models or specifically deep learning inference on edge nodes. This workload becomes popular due to the increased number of smart cameras and smart voice assistants. These devices generate a significant amount of data that has to be processed in real time. An example task will be image classification. We feed an image to the DNA model and output is class. AI workloads are computationally intensive. A typical DNA model performs hundreds of thousands, millions of floating point operations per inference. IoT devices are resource constrained, so to process computationally intensive workload, IoT applications often employ one of the two computing paradigms. IoT devices with networking capabilities such as Wi-Fi use a two-tier cloud architecture shown in the left figure. In this scenario, the device transmits data to the cloud for processing. For example, thermostat, smart switch, and smart light are IoT applications using this paradigm. On the other hand, some IoT applications use a three-tier paradigm. For example, battery-powered IoT devices such as smart door locks use a low-power wireless protocol such as Bluetooth. It then relies on an intermediate edge node to transmit data to the cloud. Recently, the emergence of specialized edge accelerators has changed this paradigm. By leveraging specialized edge accelerators, each tier can have both tier processing capabilities and less reliance on higher level tiers. Let's see some examples of traditional edge node and edge accelerator. Raspberry Pi shown in the left figure is an example of traditional resource-constrained edge device. Raspberry Pi 3B Plus has a 64-bit core processor and 1 GB memory. It's loaded with Raspberry Pi operating system and can work as an independent computer. The right figure shows NVIDIA Jetson Nano, which also has a core processor, 4 GB shared memory, and integrated with an NVIDIA 128-core Maxwell GPU. In this paper, we aim to answer the following questions. First, what are the price, performance, and energy benefit offered by edge hardware accelerators when compared to general-purpose edge and cloud computing? Second, how should modern IoT applications exploit the distributed processing capabilities of specialized edge nodes and the cloud by using various types of split processing? Third, how suitable are edge accelerators for supporting concurrent edge applications for multiple tenants? We are going to answer these questions through empirical experiments. We list the edge accelerators we use in our experiment. First is the Intel's Neural Compute Stick 2 Vision Process Unit or VPU. It consumes 1 to 2 watt power and has 512 MB memory. It costs $99 and mainly focuses on accelerating computer vision workloads. Google's Edge TPU consumes 5 to 2 watt power and has only 8 MB memory. It costs $75 and requires the models to be A/B quantized. Edge TPU and VPU work as co-processors and cannot work as independent edge nodes. NVIDIA Jetson Nano can be considered as an edge node loaded with a small GPU. It's loaded with Unix system and can work as an independent edge node. That's why it consumes more power than the VPU and Edge TPU. And it also has larger memory but similar price. Jetson TX2 is similar to Nano, but with larger memory and GPU capacity, and of course, higher cost. To ensure a fair comparison across hardware platforms, we run the same models on all platforms and subject them to the same inference workload. We use 5 DNN models in our experiment, including image classification, object detection, and keyword spotting. We run these models on edge class device, server class device, and accelerators that we showed before. We use AWS P3.2x large instance to represent a server class device. The instance also includes an NVIDIA Tesla V100 GPU, and we use Raspberry Pi 3B Plus to represent edge class device. Our first experiment involves comparing wrap and normalized performance and power of specialized edge nodes to more traditional edge and cloud architectures. The left figure shows the throughput for all of the platforms when running MobilaNet and InsertionNet v4 for image classification. Note that the figure is in log scale as the difference between the highest throughput device and the lowest throughput device is huge. Not surprisingly, the cloud GPU achieved the highest throughput and the edge device has the lowest throughput. Cloud CPU has a 10x higher throughput than Raspberry Pi, but interestingly, most of the edge accelerators can achieve similar throughput as cloud CPU. We also measure the power consumption of the accelerators, and the results are shown in the right figure. The edge TPU achieved the lowest power consumption when running Insertion v4, and the power consumptions of cloud CPU and cloud GPU are 131 watt and 111 watt respectively, which are 2 orders of magnitude higher than that of edge accelerators. Next, we normalize our measurement. The left figure shows throughput per watt for classification workloads. The cloud CPU achieves poor throughput per watt here. Even Raspberry Pi outperformed the cloud CPU. The results show that the edge accelerators are significantly more energy efficient than cloud CPU. Recall that in raw throughput comparison, edge accelerators have similar throughput with cloud CPU and smaller throughput than cloud GPU. But in the normalized results, edge accelerators has 2 orders of magnitude larger throughput per watt than cloud CPU and similar throughput per watt with cloud GPU. Edge TPU even has 1 order of magnitude larger throughput per watt than cloud GPU when running MobileNet v2. This shows the energy efficiency of edge accelerators. The right figure shows throughput per dollar of the devices. Again, the figure is plotted in log scale. The results show that edge accelerators have 10 to 100x higher throughput per dollar than cloud CPU and GPU. That means if you are planning to buy some devices for serving highly distributed deep learning workloads, edge accelerators might be a better choice than traditional cloud CPU and GPU. Next, we evaluate the benefits of hardware accelerators for distributed or split processing for edge-based deep learning workloads. We consider both model splitting and model compression, which are 2 types of split processing that have been proposed. Model splitting allows a deep learning model to be split across multiple nodes within or across tiers. We focus on sequential splitting in this work. In sequential splitting, the first k layers of the n-layer model run on the first node accelerator, and the remaining n-k layers run on the next node or tier. Model compression is another way of split processing. In this case, a full deep learning model is compressed through model distillation or pruning to construct a smaller but less accurate model. We run this compressed model on a lower tier node with less resource, and the full model on higher tier node with more resource. An inference is first run on the compressed model and produce a probability or confidence value along with each inference result. The method then uses a threshold parameter to determine if the output of the compressed model is confident enough. If it is, the output is assumed to be final. Otherwise, the input data is sent over network to the full model for a second inference. Let's consider model splitting first. Model splitting can offer 2 benefits. First, we can get bandwidth saving if the intermediate output size is smaller than the raw input size. The raw input is often in one of the 3 formats. First, compressed lossy format, such as 3PAT. Second, compressed lossless format such as PNG. Third, uncompressed RGB format. We compare the size of this write input format with the intermediate output of each layers of two typical DNNs. For MobilaNet v2, we can see that most of the layer output size are less than compressed lossless write input size. Splitting the model at layer 10 achieves nearly 8x network saving over using lossless compression for a no-split model. However, for in session v4, most of the layer output sizes are larger than the write input. We cannot get bandwidth saving in this case. So the only benefit for splitting in this case is we have a model that's too large to fit into the memory. In this case, we have to split the model. Next, we consider model compression. We use small, medium, and large models that run on device, edge, and cloud, respectively. We consider two scenarios in this experiment. A device edge case where the small model runs on the device tier accelerator and the medium model runs on the edge tier accelerator. An edge cloud case where the medium model runs on the edge tier accelerator and the large model runs on the cloud tier accelerator. The left figure shows the network bandwidth usage for both scenarios under varying threshold. A lower threshold means we are setting predictions with lower confidence from the smaller model. This achieves a larger bandwidth saving, but it's also less accurate. As the threshold increases, most inference requests fail to meet the desired confidence using the compressed model, and the requests are sent to the next tier, which increases the network bandwidth. Note that in our experiment, the edge cloud case always achieves higher bandwidth saving. That's because the medium model running on the edge tier has more confident predictions than the small model. Model compression may also achieve latency reduction. As shown in the right figure, for device edge, splitting can achieve latency reduction if the threshold is less than or equals to 0.2. For edge cloud case, splitting can achieve latency reduction if the threshold is less than 0.5. In previous experiment, we used ImageNet validation set as input data, which includes a wide range of images. We also consider a scenario where the inputs are not random but skewed towards the common case. One example for this workload might be indoor surveillance camera, where most of the frames are similar. The compressed model is well trained for frequently occurring inputs. As shown in the left figure, model compression achieves much lower latency than no-split inference for a wide range of threshold values, since it performs inference well for the common case, and avoids a second inference for the majority of inputs. We also evaluate the impact of the network latency for this case. We vary the cloud latency from 20 milliseconds to 200 milliseconds and measure the latency of using model compression relative to the no-split case. As we can see in the right figure, the higher the latency to the cloud server, the greater the benefits of using the compressed model to perform a single local inference. Next, we explore the multi-tenancy capabilities of the edge accelerators. The motivation for this is, unlike clouds that are built using large data centers, edge clusters are more resource constrained than traditional clouds. So the ability to share servers across multiple users and applications is crucial for edge. As shown in the figure, the Intel NCS2 VPU can support 8 concurrent models despite being more memory constrained than the GPUs. JSON Nano can support only 2 concurrent models, even though it has 4 GB memory. This is because the memory on JSON devices are shared across host and GPU. On the other hand, CUDA's software framework is designed for more general use and therefore more heavyweight. Loading CUDA libraries and runtime often consume more memory than the DNN itself. This is similar for JSON TX2, but TX2 has 8 GB memory, so it can load 4 concurrent models. Interestingly, Edge TPU can load a limited number of models concurrently, even though it only has 8 MB memory. That is because it automatically performs context switch between models on demand. So as long as the total memory size do not exceed the host memory, Edge TPU can load as many models as we want. However, this also introduces context switch overhead for consecutive requests of different models. That's why we see the throughput decrease when loading more models. In conclusion, in this work, we explore the benefit of using edge accelerators for AI-based workload at the edge. We first compare the throughput, power consumption, and cost of these accelerators with edge and cloud tier device. We show that edge accelerators might be a better choice over traditional edge device and cloud server in terms of throughput per watt and throughput per dollar. We show that the benefit of model splitting is highly model dependent. For models with small intermediate outputs, splitting can achieve great bandwidth saving. For models with large intermediate output, the only reason for splitting is the model is too large to fit into the memory. For model compression, we show that it can not only achieve bandwidth saving, but also latency reduction. And finally, we show that different edge accelerators can achieve different level of concurrency. The degree of concurrency depends on the edge device memory, model size, framework software overheads, and system optimizations. And that is our research work. Thank you so much for listening.